So we were discussing in the last class about the different types of feedback. So I told you clearly based on the mixing network type and sampling network type, you will have four possibilities, four possible combinations: voltage series, voltage shunt, current series, and current shunt. So we are seeing how from the name we can draw the equivalent circuit for the amplifier, and we are finding what is the effect of input resistance and output resistance because of applying negative feedback. See, here we are not considering any specific amplifier, transistor or FET. We are not considering anything. We are considering a very general amplifier. Okay, so this dotted box can have a BJT, it can have a FET, it can have a MOSFET, it can have anything. So this is a generalized diagram for an amplifier. So an amplifier will have an input impedance Ri and output impedance R0. So type of amplifier, it may be an voltage amplifier or current amplifier or trans conductance amplifier or trans resistance amplifier. So depending on that, this current source or voltage source will change. So now we are into the fourth type of feedback. It is called as voltage shunt feedback. So as the name, see, voltage shunt, voltage represents the output side. So output side I have voltage source. And shunt, current gets flowed in shunt. So you will be mixing the feedback signal in shunt. So possibility is current source because voltage is same in shunt, only current is added in shunt, right? So I'll be mixing the feedback signal in the opposite sense because it is negative feedback. So the current direction will be opposite. Okay, so see here IS and RI is the input impedance of the amplifier, and VI is the voltage, input voltage of the amplifier, and II is the input current to the amplifier. And this feedback signal IF is equal to beta V naught is mixed in the opposite sense. So the current direction will be opposite to that of your source current direction. And output side, you see, you have an voltage source. Whenever you have an voltage source, you will be having a series resistance R naught, and the voltage source value V is equal to IR. So it depends on R is going to be RM, RM is your trans resistance, and IE is going to be II. II is going to be the input current. And I'll be having a load resistance RL. I'll be measuring the output voltage across my load. So current flowing out of your amplifier is going to be I naught. Okay, always current flowing out of your amplifier is denoted by I naught. And this I, for computing the output resistance, we'll be using this I. For now, this I does not have any role to play. Okay, so this amplifier is a trans resistance amplifier. So it will have a parameter called RM. So we have to measure what is called as RM. So whenever see we will be giving standard examples of all the types of feedback amplifiers. So you need not mug up anything. Voltage series now only these amplifiers will come as voltage series. Voltage shunt now this amplifier is an voltage shunt amplifier. Like that we will be discussing examples. So you need not worry about how to identify the amplifier, what configuration it is there. All you need not worry. So whenever, for example, an emitter follower or common collector amplifier is a voltage series feedback. So it is always voltage series, it will not change. So whenever a common collector circuit or an emitter follower circuit is given in the question, it is understood that it will definitely be only voltage series feedback. So it cannot come under any other feedback type because an amplifier will fit into only one among the four categories: voltage shunt, voltage series, current shunt, current series. Okay, a single amplifier cannot come under multiple feedback type categories. So be clear on that. So definitely for one feedback, you'll have only one configuration of amplifier. You have to be very clear on that. Okay. So now we are going to find the input resistance. So input resistance, you see here you have three currents. Here I can do nodal analysis. One current IS is coming. Two currents II and IF are going out from the node. So I can write IS is equal to II plus IF. This is a basic Kirchhoff's current law equation. So whenever you have current source, definitely you will be made to apply KCL. Whenever you have voltage source, you will be forced to apply KVL. That will make your job simple. And II plus IF is equal to beta V naught. So I am replacing IF by beta V naught. So IS is equal to II plus beta V naught. Again, you see, I am having V naught here in this equation, which is unknown here because IS belongs to input side, II belongs to input side, V naught belongs to output side. So I have to find V naught and relate that with the input side.